Now we can see about decimation. What is meant by decimation? Decimation reduces the sampling rate effectively by compressing the data and retaining the desired information. And also it is indicated by the symbol, that is downward arrow mark of D. Therefore, if you are giving the input x of n, it can be given as y of n equal to x of d into n. And decimation by a factor D. Decimation by a factor D means to reduce the sampling rate. Now we are considering the signal x of n, and it is having the spectrum of x of omega. It varies from the interval 0 less than or equal to modulus of omega less than or equal to pi. And here we are taking the sampling frequency as fx and the maximum frequency range is f max. And we know that it can be related as f max is greater than or equal to 2 f max. Therefore, f max is less than or equal to fx by 2. Now, this is the block diagram for the decimation by a factor D. Here we are giving the input x of n and the anti-aliasing filter, and the output and the impulse response is given as h of n, and the output is given as v of n. Where we are giving the input of this downsampler as y of m. It is given, we are downsampled the signal, and finally we are getting the output. Here now we can see the derivation of the decimation by the decimation equation. Now from the figure we know that the output of the filter is a sequence v of n, and it is given as v of n equal to x of n into our convolution h of n. Why we can determine this by using the convolution formula as v of n equal to summation of k equals 0 to infinity h of k into x of n minus k. Let us mark this as equation 1. When v of n is downsampled by a factor d, we get y of n equal to v of m into d. Therefore, now we are replacing this n equal to md in the first equation. Therefore, we get y of n equal to summation of k equal to 0 to infinity h of k into x of md minus k. It is marked as equation 2, and this gives the output equation of the signal. Now let us relate the spectrum between x of n and y of n. Let us take this v of n. This is the input sample, and p of n is the pulse train signals. Now we are convolving the two sequence. Then output is given as v cap of n equal to v of n into p of n, and it is represented in figure C. Now let us derive the output spectrum by using the decimation equation. Step 1. Now here the downsampled equation, it is given as v cap of n equal to v of n into p of n, where v of n is the output of the filter and p of n is the pulse train of impulse. And here y of m is given as v cap of m into d. Let us take the z transform for the same equation. Therefore, it is given as y of z equal to summation m equal to minus infinity to infinity y of m into z power minus m. And also here we know that y of m equal to v cap of m into d. Therefore, we can give us y of z equal to summation of m into minus infinity to infinity v cap of m into d into z power minus m. It is marked as equation 3. Now, for simplification, let us take md equal to p, and if we know that if m tends to infinity, p also tends to minus infinity, and if m tends to minus infinity, p also tends to minus infinity. Therefore, the above equation can be written as y of z equal to summation p equal to minus infinity infinity v cap of p into z power minus p by d. Here we are replacing this m by minus p by d. Now we are changing the damping variable p to m. Therefore, we are getting the equation. It is marked in equation 4. Now let us take the equation 1. We know that v cap of n equal to v of n into p of m. In this equation, we are replacing this n equal to m. Therefore, v cap of m equal to v of m into p of n. It is marked as equation 5. Now we are substituting this equation 5 in equation 4, and therefore we are replacing in the place of v cap of n is replaced by v of n into p of n in equation 4. Therefore, it is marked as equation 6, where we know that p of n is the periodic strain of impulse, and it is represented by using the discrete time Fourier series, and it is shown in equation 7. Now let us substitute the value for 7 in equation 6. Therefore, we are getting the value of y of z equal to summation m equal to minus infinity to infinity v of n into 1 by d summation k equal to 0 to d minus 1 e power j 2 pi km by d into z power minus m by d. But now we are interchanging the order of summation. Therefore, we are getting the equation by interchanging the order of summation. We are getting the equation as y of z. Now let us relate this to the standard formula for y of z transform. Therefore, we can write the term inside the summation as v of e power minus j 2 pi k by d into z power 1 by d. This is marked as equation 8. Now, to find the spectrum, we are just replacing this z equal to e power j omega y. Y omega y represents the frequency of y of m. Therefore, in the above equation, we are just representing this by using this z is replaced by e power j minus j omega y. Now, in the second equation, we are just grouping this e power term, and finally we know that h of e power j omega can be written as h of omega. Therefore, by using the equation, we are just interchanging and simplifying the equation, and it is marked as equation 11. And this equation indicates the replicas of x of omega y by d at regular intervals of 0, 2 pi, 4 pi and 6 pi. Now, we want to reduce this equation, therefore simplify this equation. Therefore, we are just putting k equal to 0 in equation 11. Therefore, we are getting this y equation as y of omega y equal to 1 by d x of omega y by d into h of omega y by d. And here we know that h of omega by d is the properly we are designed to avoid the Ising effect. We are taking that quantity equal to 1. Therefore, the equation can be reconstructed as y of omega y equal to 1 by d x of omega y by d, and which varies from the interval to 0 to pi. And this is the equation which relates the spectrum of x of n and y of n. Thank you.